You know, usually when we talk about a medical diagnosis, there's this expectation of absolute precision. You break your arm, the X-ray shows that jagged white line, and the doctor just points at it, broken or not broken.
Right. It's super clean.
Exactly. It's clean, it's binary, and it's isolated to that one specific bone. But when we transition into enterprise infrastructure, specifically moving from a quick sandbox environment into a global multi-region deployment, that X-ray machine just shatters completely.
Oh, 100%. You are not dealing with a clean break anymore.
No, you're really not. We start looking at a deployment landscape that is profoundly murky, highly interconnected, and frankly incredibly fragile if it isn't architected correctly from day one.
I mean, it is the absolute definition of diagnostic muddy waters.
Mm.
If you were looking at infrastructure as code that was, just duct taped together for a single test run, and you are suddenly tasked with forcing that exact same code to scale across a massive enterprise, you are going to hit a wall. Hard.
Which is exactly why we are here today. For this deep dive, our primary mission is to systematically dismantle a rigid, hard-coded infrastructure prototype and, well, rebuild it for scale.
Yeah, we're doing a full teardown.
Complete teardown. We were pulling directly from the SAP training materials, specifically analyzing Unit 3, Lessons 1 and 2, which focus on SAP Business Technology Platform, or BTP, deployments via Terraform. And for this discussion, I'm going to put on my Senior SAP Enterprise Architect hat.
Meaning you get to point out all the flaws.
Basically, yeah. I'll be focusing on the core structural logic, the DRY principles, don't repeat yourself, and the architectural dependencies of parameterized infrastructure.
And I'll be playing the role of the lead basis and functional engineer. So my focus is the execution layer. We are going to dig deeply into the exact configuration paths, the directory structures, the internal mechanics of the HashiCorp configuration language, and the specific CLI commands you need to run to physically deploy these resources into SAP BTP.
Right, we're taking the theory of those SAP training modules and translating them into the harsh reality of an enterprise terminal.
Because the terminal does not care about your theory. It only cares about syntax.
Exactly. So, look, if you're listening to this and you've ever spun up a quick BTP trial account for an afternoon of testing, you've probably just hard-coded your global account ID or your region directly into your configuration file.
We've all done it.
We has, and it works perfectly for a Tuesday afternoon sandbox. But think about what happens when that exact same code base needs to deploy across a massive organizational topology. You've got dev, test, QA, pre-prod, and prod environments.
Right. You are deploying into Frankfurt, Virginia, Singapore.
Yeah, and suddenly that rigid code is a massive liability.
It becomes a maintenance nightmare almost instantly. I mean, I've seen organizations where developers end up copying and pasting entire directory structures, just maintaining 50 identical folders, where the only difference is like one single string of text representing the region.
Which is horrifying.
It completely defeats the purpose of automation. You aren't managing infrastructure as code at that point. You are just managing text files manually, and you're basically praying you don't make a typo.
So let's unpack the architectural shift required to actually fix this. As an enterprise architect, the very first thing I look at when reviewing a team's Terraform codebase is the separation of configuration logic from execution state.
The cardinal rule.
It really is a fundamental law of scalable infrastructure. If you are setting up an SAP BTP subaccount and you have hard-coded the global account right there in your provider block, or you've hard-coded the region directly in your main configuration file, you have created a monolith.
A very brittle monolith.
Exactly. That code cannot be handed off to another development team. It cannot be integrated into a CI/CD pipeline because the configuration itself dictates the environment.
You've essentially locked the definition of the infrastructure to a single, immutable instance in space and time. The Terraform engine parses that file, sees the hard-coded region, and builds a static graph.
Right.
And to break that monolith, we have to introduce a dedicated abstraction layer.
Right.
And in the Terraform ecosystem, that abstraction layer begins at the most foundational level, which is variables.
Yeah, when you configure a Terraform provider for multiple environments, extracting that hard-coded global account into a variable block isn't just a suggestion. I mean, it's an architectural mandate.
You literally have to do it.
Because without it, you simply cannot use the same code base to deploy to a developer's trial account and a highly secure, productive enterprise global account. The blast radius of trying to manage those environments with separate, diverging code bases is just way too high.
Oh yeah. You end up with configuration drift, where production looks completely different from
And
development.
that's exactly when deployments fail catastrophically.
So shifting to parameterization requires a very specific approach to how we structure our files. While Terraform's core parser will technically read any file ending in .tf within a directory and concatenate them into one giant virtual file in memory.
Which is a cool trick, but dangerous.
Very dangerous. We do not just scatter variables haphazardly throughout our main configuration file. Separating your variable definitions into a dedicated file, universally named variables.tf, is a strict, non-negotiable best practice for readability and collaboration.
I always tell my teams that the variables.tf file acts as the API documentation for your infrastructure module. If I am pulling your module from a private registry, I shouldn't have to read through, 500 lines of resource definitions just to figure out what inputs you need from me.
No one has time for that.
Right, I should be able to open that one variable file and immediately understand the contract.
That concept of a contract is exactly how you execute this. You open your IDE, create that new variables.tf file, and begin defining your blocks. You start with the keyword variable, followed by the name of the variable, establishing that signature.
But an empty block is useless.
Right, completely useless. Inside that block, you have to define the type constraint, because Terraform is strongly typed behind the scenes. It handles primitives like strings, numbers, and booleans, but it can also handle incredibly complex structural types like nested maps of objects.
Though for something like a BTP global account, we are enforcing a strict string type.
Exactly. The type constraint prevents someone from accidentally passing, say, a list of global accounts when the SAP BTP provider is only capable of authenticating against one at a time. It's your first line of defense.
But beyond the type, the metadata is equally critical.
Oh, absolutely.
Yeah.
You must assign a description attribute. Writing out clearly that a variable represents the subdomain of the BTP global account tells the caller exactly what is expected.
Because a variable named just account could mean literally anything.
Exactly. But we also have advanced flags we can throw in there. For instance, if you are passing a database password or an API token, you flag the variable as sensitive.
Oh, that is crucial.
It really is. This instructs the Terraform engine to obfuscate the value in the terminal output and in any CI/CD pipeline logs. It prevents secrets from being written in plain text to standard output.
Which is a massive security requirement for any enterprise deployment. I mean, you can also mark a variable to ensure it cannot accept a null value, forcing the downstream resources to always have data to work with. But once we have this blueprint established in variables.tf, the physical act of refactoring requires us to go back into the main configuration and actually rip out the hard-coded data.
Right. You navigate back to your provider.tf file or your main.tf, locate the BTP block, find where you pasted your global account string last week, and you delete it.
Just highlight and backspace.
Gone. You replace it with the reference syntax pointing directly to the variable you just created. So it looks like var.global account.
Yeah.
From that moment on, the provider configuration is dynamic. It will wait to authenticate until it dynamically fetches whatever value is passed into that variable at runtime.
Now, I look at the training materials for this unit, and there is an option introduced here that, frankly, always sets off alarm bells for me as an architect.
I think I know where you're going with this.
The concept of applying a default value inside the variable definition. The idea is that if a user doesn't provide a global account, it defaults to, say, a specific trial account string just to make the module easier to run out of the box.
Right, to make it easy for the dev approach.
Exactly. But if we apply default values to make a module easier to call, aren't we essentially masking required inputs? If a deployment pipeline fails to inject a parameter because of a scripting error, the system will just silently fall back to the default.
Which is terrifying.
We could accidentally deploy production resources into a trial region, or rack up billing charges in the wrong global account entirely.
It is one of the most dangerous anti-patterns in infrastructure as code. Default values make a variable entirely optional for the calling system. Terraform calculates its directed acyclic graph, the DAG, based on available inputs.
Right.
So if you define a default value for your BTP region as like US 10, and your production deployment pipeline fails to inject the intended 11 string, the Terraform binary won't throw an error. It won't halt.
It just keeps going.
It happily calculates the graph, generates a plan, and executes the creation of your SAP infrastructure in the completely wrong geographic location.
It basically assumes silence equals consent to use the fallback.
Which is unacceptable for enterprise state management. Therefore, when you are designing modules that will run in CI/CD pipelines, you must strictly reserve default values for attributes that genuinely represent a safe, universally applicable baseline.
Like what?
Something like a Boolean flag for a minor feature toggle. But for environment-specific data, your global account ID, your deployment region, your organizational cost center, you must omit the default value entirely.
Yeah, by omitting the default, you elevate that variable to a mandatory input. If the caller doesn't provide it, the Terraform parser fails immediately during the initialization or plan phase with a fatal error. It physically cannot compute the graph.
And failing fast before any API calls are made to SAP is exactly the behavior you want.
Exactly. Which brings us to the execution reality. If default values are too dangerous for environment-specific data, and we've stripped them out of our variables.tf blueprint, how are we securely and systematically injecting the correct values at runtime?
This is where we transition from the configuration layer to the state injection mechanism. We need to talk about the .tfrs file.
Let's frame this conceptually for the listener. If the variables.tf file is the architectural blueprint defining what is mathematically possible for your infrastructure, the .tfrs file represents the actual concrete reality being injected for one specific execution run.
Right, it's the state of the world right now.
It is the snapshot of the environment you are targeting.
It's the physical payload. This separation is what allows a single module, a single Git repository containing your infrastructure code base, to be invoked 100 different times using 100 different .tfrs files to deploy into 100 different SAP BTP subaccounts across the globe.
So let's talk about the mechanics of how Terraform actually ingests this reality. When you run a command against a specific SAP BTP trial account, you have to feed those mandatory variables into the engine, because without them, Terraform's graph theory breaks down. It just can't resolve the dependencies.
By default, when you execute a Terraform plan or a Terraform apply in your terminal, the core engine initiates a scanning process in your root directory. It is explicitly looking for a file named exactly terraform.tfrs.
Not variables.tfrs, not myconfig.tfrs.
Exactly, just terraform.tfrs. It also looks for any file ending with the .auto.tfrs extension. If it detects these files, it automatically opens them, parses the key value pairs inside, and maps them to the corresponding variable blocks you defined in your blueprint.
It's worth noting for the listener that there is a strict precedence hierarchy here. You can pass variables via environment variables in your operating system. You can use the terraform.tfrs file. You can use the auto.tfrs files, or you can even pass them directly in the CLI using a specific flag like -var.
Right, which gets chaotic if you aren't careful.
Exactly. If you define the region in 3 different places, Terraform has a mathematical order of operations to decide which one wins. Usually, the direct CLI flag overrides everything else, followed by the .auto.tfrs files, and then the standard terraform.tfrs file.
But for our SAP scenario, we are sticking to the standard terraform.tfrs file. In our main configuration, we have a resource block defining an SAP BTP subaccount. It currently has a bunch of hard-coded strings for the subaccount name, the subdomain, the geographic region, a Boolean flag for whether beta features are enabled, the environment stage, and a cost center code for billing.
Our first architectural action is to extract every single one of those into our variables.tf file as distinct, strictly typed variable blocks. We establish the API signature, and like we said, we leave the defaults completely empty for critical routing data like the global account and the subaccount name, forcing them to be mandatory inputs.
Next, we create that new file in the directory named terraform.tfrs, and the syntax inside this file completely shifts.
It's not HCL anymore, really.
No, you are no longer writing complex HCL blocks with curly braces and type definitions. It is a pure, simple key value assignment document. You literally write the variable name, an equal sign, and the string.
Just region equals 10.
Exactly. You explicitly paste the string of your specific BTP trial account right there. You define your region, perhaps explicitly setting it to the string representing the US East trial region.
Now, as you move back into your main configuration file to replace all those old hard-coded strings with the new variable references, the risk of human error skyrockets. Making mass text replacements across a complex, multi-hundred-line configuration file is historically where deployments go to die.
Oh, without a doubt.
You miss one underscore and the whole deployment pipeline halts.
This is where execution tooling becomes paramount. You not just rely on manual typing. You leverage your integrated development environment, or IDE. If you are using a modern editor like VS Code with the official HashiCorp Terraform extension installed, the language server is running in the background.
Constantly watching what you do.
Right, actively parsing your variables.tf file in real time. As you go into your resource block and start typing the reference prefix var, The IDE will instantly provide type-ahead auto-completion suggestions.
It's a lifesaver.
It knows exactly which variables you just defined, and it knows their data types. You use those suggestions to completely eliminate syntax typos during the refactoring process.
It builds a safety net into the authoring phase. But we need to look at the vulnerability we've just opened up on the execution side. We are now allowing external callers, whether that is a human engineer running commands on their laptop or a headless CI/CD pipeline script pulling from a secret manager, to inject values dynamically via this .tfrs file.
Right.
We have solved the hard coding problem, but we've introduced the human input problem. What happens when a junior developer on a Friday afternoon inputs US 11 instead of a valid BTP trial region?
Well, on a baseline level, Terraform's type constraint mechanism will accept the string US 11 without blinking. It satisfies the requirement that the input must be a string.
Right, it doesn't know SAP geography.
Exactly. The Terraform engine will construct the internal graph, build the massive JSON payload required for the API request, and send it across the network to the SAP BTP backend. It is only at that point, during the physical execution phase, that the SAP API will reject the payload.
Usually throwing a nasty 400 bad request error.
Right, returning an HTTP error code, which causes your deployment to fail midway through an apply operation.
Which, from an architectural standpoint, is disastrously late in the life cycle. I need my infrastructure deployments to fail fast and fail early. I cannot trust the caller of the module to inherently memorize our organizational naming conventions, or to have the SAP BTP documentation open to cross-reference exactly which strings are valid for which regions.
We cannot rely on hope as a strategy.
No. We have to build guardrails directly into the configuration itself. This is the essence of compliance as code.
We need to enforce governance before the Terraform binary even attempts to negotiate a network connection with SAP, and we achieve this natively using the validation block.
This is one of my favorite features.
It's so powerful. This allows us to embed custom logical rules directly at the variable definition level, mathematically guaranteeing that non-compliant data never makes it past the local planning phase.
Think of validations like a bouncer standing at the heavily fortified door of our SAP BTP landscape. Before Terraform is even allowed to construct an API request, before it even attempts to reach out over the network, that bouncer demands to see the ID.
Let me guess. The ID is the .tfrs input.
Exactly. The ID is the value being injected from the .tfrs file. The bouncer checks the ID against a strict list of organizational rules. If the cost center code provided isn't exactly 5 digits long, the bouncer denies entry. The process halts immediately on the developer's laptop, saving us from a pipeline failure and a corrupted state file.
So let's execute that bouncer logic in code. A validation block is a nested structure placed directly inside your existing variable block. It requires 2 absolute attributes to function: a condition and an error message.
And if you miss either one, the parser fails?
Correct. The condition relies on Terraform's internal expression language. It must evaluate down to a strict Boolean true or false. If the expression evaluates to true, the input is deemed compliant and the engine moves on. If it evaluates to false, the run halts immediately, and the exact string you defined in the error message attribute is printed as a fatal error in the terminal standard output.
Let's apply this to our region problem. We need to enforce a policy that anyone deploying this specific module to a trial account is only physically permitted to use the approved trial regions. How do we actually write that rule?
Inside your variables.tf file, within the block for the region variable, you nest the validation block. For checking against a known list, we use the native contains function. You write a condition that passes a hard-coded list of the allowed strings, perhaps use10, u10, app10, and then you pass the incoming variable as the item to search for.
Like contains list var.region.
Exactly. The function checks if the injected string exists within that strict array.
And if it doesn't?
The function returns false. The engine catches that false Boolean, halts the graph calculation, and prints your custom error message. Something explicit like, the provided region must be a valid SAP BTP trial region. So if the developer typed US 11, they see exactly why their plan failed within milliseconds without ever touching the SAP backend.
We can apply that exact same logic to our environment stages. We only ever want 3 environments authorized in our architecture: development, testing, and production. We use that same contains function to check the incoming stage variable against that strict list of 3 strings.
Right. Dev, test, prod.
Yeah. If someone tries to deploy a sandbox or a CAW environment, the validation catches it and fails the build.
We are shifting the compliance check as far left as mathematically possible, But we can push the complexity even further. Let's look at the billing cost center variable.
Oh, this is a fun one. In a massive enterprise scenario, finance departments are absolutely ruthless. They dictate that every single piece of cloud infrastructure must be tagged with a billing cost center, and that cost center must adhere to a strict legacy format.
Usually something really specific.
Yeah, let's say it has to be exactly a 5-digit number. No letters, no hyphens, no special characters, exactly 5 numbers. How does our Terraform bouncer validate that level of granularity?
For complex pattern matching, we have to leverage regular expressions or rejects. Inside the validation block for the cost center, we combine two functions. First, we use the regex function to define the pattern.
Which can be a bit cryptic to read.
Regex always is. We write a pattern that asserts the absolute start of the string, specifies that the characters can only be digits from 0 to 9, mandates that there must be exactly 5 of those digits, and then asserts the absolute end of the string. So it looks something like 09bet.
It's mathematically guaranteeing the shape of the data.
Exactly. We then wrap that regex function inside the can function. The can function evaluates an expression and simply returns true if it executes without an error and false if it fails.
Ah, I see.
So if the pipeline injects the string 12345, the regex finds a perfect match, no errors occur, can returns true, and the deployment proceeds.
But if they mess up?
If the pipeline injects 1234A, the regex throws an error, because of the letter, catches the error and returns false, and the validation bouncer halts the entire deployment, printing an error that the cost center format is invalid.
We have literally codified corporate finance policies directly into our infrastructure blueprint. That is the true power of infrastructure as code at an enterprise scale. It's not just about spinning up servers faster, it's about embedding your organizational governance into the compiler itself.
To verify this hands-on, you drop into your local CLI. You don't just run and apply. The first command you execute is Terraform FMT.
Format.
Yes, FMT for format. This is a critical code hygiene step. It scans your files and automatically formats the syntax, aligning the equal signs and ensuring perfectly consistent indentation across all those nested validation blocks. It makes the code readable for the next engineer.
Once it's formatted, how do we prove our logic holds?
You execute Terraform validate. This is a powerful offline command. It performs a rigorous static analysis of your configuration directory. It does not attempt to contact the SAP BTP backend. It doesn't even need internet access.
Really? Just completely offline?
Yep. It parses your HCL syntax, verifies that all your variables are mapped correctly, and ensures that your functions and regex patterns are structurally sound. It builds the graph locally to check for circular dependencies.
And assuming the static analysis comes back clean with no syntax errors.
Then you run Terraform plan. This is where the engine compares your configuration against the state file and the actual reality of the cloud environment. And what is profoundly important here is the expected output.
Because we didn't actually change what we're building.
Exactly. Because our objective was to refactor, to replace hard-coded values in the main configuration with parameterized variables that are currently being fed those exact same string values via our .tfrs file. The mathematical state of the infrastructure hasn't changed.
The blueprint is different, but the house we are building is exactly the same.
Which means the CLI output should explicitly state that there are no changes required. The infrastructure is up to date. The graph calculated by the variables perfectly matches the graph that was originally hard-coded. Seeing that no changes output is the ultimate confirmation that your refactoring operation was executed flawlessly. You haven't accidentally altered the intended state of the cloud environment. You've merely abstracted the delivery mechanism.
Okay, so our inputs are thoroughly protected by our validations. We have our bouncer checking IDs. But as I review this architecture, a new, more subtle problem is emerging.
What are you seeing?
Well, we've introduced variables to make the code dynamic, but our main configuration file still requires redundant inputs that are essentially just minor string variations of one another.
Oh, I see where you're going.
Yeah. For example, to create this BTP subaccount, we are forcing the caller to provide a project name, but we are also forcing them to explicitly provide a subaccount name and a subdomain string. In a mature enterprise, a subaccount name isn't a random string. It's almost always a strict concatenation of the environment stage and the project name. Something like dev project alpha. Why are we asking a human engineer or a pipeline to manually type that out and risk introducing typos?
We are blatantly violating the DRY principle. Don't repeat yourself. We are forcing the user to calculate the naming convention in their head before they populate the .tfrs file.
To eliminate this redundancy and protect the integrity of our naming conventions, we have to stop treating every single required parameter as an external variable. We must introduce programmatic internal transformations. We need to shift the burden of calculation from the human to the Terraform engine by utilizing local values.
This represents a vital conceptual distinction in Terraform architecture. A variable, which we define in the variables.tf file, is an external input. It is data provided from the outside world by the caller. A local, which is defined via a locals block, is purely internal logic. It is processed entirely within the boundaries of the module itself. It allows you to assign a temporary, internal name to a computed Terraform expression.
The caller shouldn't have to provide a subaccount name, a subdomain, and a Boolean flag for whether beta features are enabled. That is asking the caller to do our architectural thinking for us.
And they will inevitably get it wrong.
Exactly. They don't care about our internal routing logic. They just want to provide two core pieces of business data: the name of their project and the stage they are deploying to. Our Terraform architecture must ingest those two data points and programmatically derive every other required parameter internally. We enforce the naming conventions in the code, removing human memory from the equation entirely.
Translating this into execution means we have to intentionally break our existing code to upgrade it. We go back into our variables.tf file, and we ruthlessly delete the variable definition blocks for the subaccount name, the subdomain, and the beta-enabled flag.
Just wipe them completely out.
We wipe them out. We then create one single, new, external variable to represent the core project name.
And the moment you save that file, your main configuration file lights up with errors in your IDE. It's suddenly filled with broken references because it's still looking for variables that no longer exist in the API contract.
To resolve those broken references, we shift to the very top of our main configuration file. This is a crucial stylistic and structural best practice. You keep all of your local logic derivations consolidated at the very top of the file you are working in.
Why specifically at the top?
Because if you start defining local logic blocks halfway down a 1,000-line configuration file, or scattering them across multiple files, you severely degrade the readability of your module and make debugging state issues a complete nightmare. You want the next engineer to see exactly how the data is being manipulated the second they open the file. So at the top, we define a structural block.
The syntax here is notoriously confusing for newcomers, so let's really highlight it. The block itself is defined using the plural keyword locals.
Right. The block definition is plural, locals, followed by curly braces.
Okay.
But later, when you actually need to reference one of the values you computed inside that block, down in your resource definitions, the Terraform parser strictly requires you to use the singular prefix.
So you define it inside a locals block, but you reference it as local.something.
Exactly. It's a quirk of the HashiCorp configuration language that you simply have to memorize to avoid syntax errors.
Inside this locals block, how do we actually perform these internal derivations? We need to use Terraform's internal functions to build our strings. When you are establishing organizational naming conventions for 50 microservices across multiple cloud environments, you must use a locals block to concatenate the data. Relying on an end user to manually type dev project alpha correctly every single time will inevitably lead to typos.
It's guaranteed to happen.
And in SAP BTP, a typo in a subaccount name can misalign your entire routing topology and break integration with your backend ERP systems.
So we execute this string interpolation directly within the block. We define our first internal value, naming it subaccount name. We assign it an expression that takes the external variable representing the stage, adds a hyphen, and appends the external variable representing the project name.
Which looks like sivdar.stage.project name in the code.
Exactly. The Terraform engine resolves this instantly in memory. We then go down to our BTP resource block, and we change the name attribute to point to this newly computed local.subaccount name. That resolves the first broken reference.
Let's tackle something slightly more complex than just mashing two strings together. We have a Boolean flag for enabling beta features in the BTP subaccount. Architecturally, if the environment stage is prod, we fundamentally and unequivocally do not want experimental beta features enabled on that subaccount.
That would be a disaster waiting to happen.
Right. It introduces unacceptable risk to production workloads. By baking this logic directly into the local configuration, we ensure production stability without relying on a human remembering to switch a flag from true to false in a pipeline script.
We don't achieve this with clunky multi-line if-then-else statements either. Terraform's expression language supports ternary logic, which is a highly concise way to evaluate conditions in line.
How does that look in the code?
Inside our locals block, we define our beta-enabled value. We write an expression that evaluates the stage variable. It basically reads, if the variable stage is exactly equal to the string prod, then set this local value to the Boolean false.
And if it's not prod? If it's dev or test?
The ternary operator uses a colon to represent the otherwise condition. We dictate that otherwise, the value should be set to true.
So it's var.stage equals prod false true.
Yes. The engine evaluates the incoming stage and instantly resolves the Boolean locally. We update our resource block to point to local.baitEnabled, resolving our second broken reference and completely automating our environment stability controls.
Now we arrive at the heavy lifting of string manipulation, the BTP subdomain. In SAP BTP, the subdomain is the unique identifier used in the URL for authenticating and accessing the subaccount. It has extremely strict character constraints enforced by the API.
Very strict.
It usually requires lowercase letters and strictly forbids spaces. But a business user might pass a project name into our module that contains capital letters and spaces, something like Project Delta. We need our infrastructure code to programmatically sanitize that raw input before it reaches the SAP backend.
This requires chaining Terraform's built-in functions together, and the engine executes them, operating from the inside out. In our locals block, we define the subdomain value. The innermost step is our basic string interpolation, mashing the stage and project name together, which results in, dev project delta.
With the capital P, capital D, and the space.
Right. Now, we wrap that entire string expression inside the replace function. We configure the function to search the string for a literal space character and replace it with a hyphen.
So the engine processes that, and the intermediate state becomes dev project delta. We've eliminated the space, but the capital P and D still violate the strict subdomain rules.
To resolve that, we take that entire nested replace function and we wrap it one layer deeper inside the lower function. The lower function iterates over every single character in the resulting string and forces it to lowercase.
Well, it's like a nesting doll.
Yeah. Exactly. The final, fully compiled syntax looks like a nesting doll. Lower, wrapping, replace, wrapping the interpolated string. The engine parses it flawlessly and outputs a perfectly sanitized string ready for the BTP API.
As an architect reviewing code, I have to pause here. This nested function lower wrapping replaced wrapping interpolation looks incredibly dense to read. Is there a point where an expression becomes so deeply nested and complex within a single local value that it actually damages the readability and maintainability we are trying to protect?
Well, that's a really common debate in code reviews.
Are we just writing overly clever code that the next engineer won't be able to decipher?
It is a highly valid concern, and it's something the official HashiCorp documentation explicitly warns against. They call the overuse of locals. If you find yourself chaining 6 or 7 functions together in a single, massive, unreadable line, it becomes impenetrable for the person taking over your code base next year.
It just becomes spaghetti code.
Exactly. You want to use locals to enforce the DRY principle and guarantee naming conventions. But if the local expression itself requires a massive paragraph of inline comments just to explain what it does, you have crossed the line into architectural spaghetti. In this specific scenario, chaining a lower and replace function is a standard enough string sanitization technique that it remains acceptable and readable.
We've sanitized the string perfectly. We have dev project delta. But this introduces a massive architectural collision point specific to SAP BTP. Subdomains in BTP must be globally unique across the entire landscape region.
They absolutely have to be unique.
If we have 2 different development squads working in the same global account, and they both decide to spin up a test environment using the generic project name alpha, their locally calculated subdomains will both evaluate to test alpha. The first squad's Terraform deployment will execute perfectly.
And the second squad?
Second squad's deployment will hit a global uniqueness conflict at the BTP API layer and fail catastrophically. We cannot just sanitize the string, we have to guarantee programmatic uniqueness.
To guarantee that uniqueness, without requiring the teams to manually invent complex names, we must introduce a new layer of automation. We need to inject mathematical randomness into the configuration. We accomplish this by utilizing the random UID provider resource.
Which is a huge shift.
It is. And introducing this resource forces us into a critical lesson on the Terraform lifecycle and the devastating nature of destructive state changes.
This is where we shift from merely formatting text strings to deeply understanding how the Terraform state engine manages the lifecycle of immutable attributes in the cloud. In SAP BTP, a subdomain ID is an immutable attribute.
Meaning you can't just tweak it.
Right. That means you cannot simply send an API request to update or edit a subdomain ID once the subaccount has been physically provisioned. If the Terraform state engine detects a fundamental change to this specific identifier in your local configuration, it realizes it cannot run a simple update call. To satisfy your new configuration, it must physically tear down the entire existing subaccount and build a completely new one from scratch.
Which is a massive, potentially catastrophic architectural risk if it happens late in a deployment cycle. Let's trace the exact execution mechanics of how this plays out. First, at the top of our main configuration file, completely outside of our locals block, we declare a new resource type.
And the syntax for that.
The block syntax is resource random MUID, followed by whatever internal name we want to give it, like MUID. This specific resource block doesn't require any internal configuration parameters. When the Terraform engine creates it, the provider binary simply generates a universally unique identifier, a UEID, and stores it in the state file.
Now we need to dynamically append that newly generated UUID to our sanitized subdomain string to guarantee it never collides with another project.
We navigate back into our locals block, right back to that complex subdomain definition. We wrap our sanitized string logic inside yet another function, the join function.
We're adding another layer to the nesting doll.
Yep. We configured the join function to combine our sanitized string, append a hyphen, and then we pass a reference directly to the output of our new random resource. We reference the generated UEID string by calling randomuid.muid.result.
Okay, so what does the final string actually look like?
So now, the fully derived local subdomain string that Terraform calculates in memory looks something like test alpha, followed by a massive 36-character hexadecimal UUID string. It is now mathematically guaranteed to be globally unique.
We have our logic locked in. We drop to the CLI to execute this refactoring. But because we've just declared a completely new resource type from a provider we weren't previously using, the random provider, we cannot just blindly jump to the planning phase. The local Terraform binary doesn't know how to generate a UUID yet.
Exactly. You must halt and run the CLI command Terraform init again.
Reinitializing.
Yes. The initialization phase scans your configuration, detects that a new provider requirement has been declared, reaches out over the network to the public Terraform registry, securely fetches the exact compiled binaries for the random provider, and installs them locally in your hidden .terraform directory. It initializes the plugins required to execute the new code.
And updates the lock file.
Right, it updates the dependency lock file.
All right.
Once that is complete, you run your standard Terraform FMT to fix any indentation drift caused by adding all these nested functions and ternary operators.
And now we arrive at the most critical, high-stakes step in this entire deep dive, the plan phase.
You execute Terraform plan.
Yeah.
And you do not just glance at the output. You must read it meticulously, line by line.
Because it's not going to be a clean output anymore.
No. The output will no longer say 0 to add, 0 to change, 0 to destroy. The terminal will highlight your SAP BTP subaccount resource block in stark red and yellow text. It will explicitly print the warning that the subaccount must be replaced.
It will literally say that in caps.
Oh yeah. You will see a highly visible -/+ symbol next to the resource identifier.
Let's explain exactly why the engine made that decision. Because the local value representing the subdomain string changed because we appended that UUID, the intended state calculated by Terraform's graph, diverges fundamentally from the actual state currently residing in the BTP cloud. The engine queries the provider schema, recognizes that the subdomain attribute is flagged as immutable, and determines that the only mathematical way to reconcile the configuration with reality is absolute destruction and recreation.
If you accept that plan and proceed by running Terraform apply, Terraform will explicitly output its execution order. It will not update your subaccount. It will first execute an API call to completely destroy your existing BTP subaccount.
It just wipes it out.
It will wipe it off the map. It will then generate the new random UID resource. Finally, it will execute a new API call to create an entirely new BTP subaccount from scratch, utilizing the newly derived globally unique subdomain string containing the UID.
And you can verify that afterwards.
Right. Once the apply operation finishes, you can validate the destruction and recreation by logging into the BTP browser interface, navigating to your global account directory, and physically verifying that the new subaccount ID perfectly matches the UID appended format.
This brings us to a concrete, potentially terrifying scenario for anyone managing cloud infrastructure. When you are refactoring code and you alter a core parameter like a subdomain ID deep inside a locals block, You must review the Terraform plan output with extreme prejudice.
I cannot stress that enough.
Because if you blindly commit that code and a CI/CD pipeline runs a Terraform apply automatically, Terraform will destroy your entire productive subaccount to satisfy that naming convention change. It will obliterate the subaccount, and with it, it will destroy all the KTA and cloud database instances, the event mesh queues, the complex destination configurations, and every single byte of productive business data residing inside it.
And there's no undo button for that.
All because you updated a local string concatenation?
It is the ultimate double-edged sword of enterprise infrastructure as code, the exact same automation engine that allows you to architect and deploy a globally scaled, highly compliant SAP landscape in a matter of minutes, is the exact same engine that can obliterate that entire landscape in seconds if you do not respect the immutable attributes of the state graph.
It's a sobering reality, but it's the reality of operating at scale. Let's step back and summarize the architectural journey we've taken in this deep dive. We started with a static, brittle configuration script designed for a single afternoon in a sandbox.
And we systematically transitioned it into a DRY, highly flexible, enterprise-grade architecture.
We leveraged variables to completely separate our configuration logic from our environment state, unlocking modular, repeatable execution across multiple stages. We implemented strict validations, putting an uncompromising bouncer at the door to mathematically ensure that any injected inputs strictly adhere to BTP compliance and organizational governance before a single API call is made.
And finally, we utilized complex, local logic to programmatically enforce organizational naming conventions, sanitize strings, inject uniqueness, and derive environment-specific risk controls, like automatically disabling beta features in production workloads.
We essentially removed the risk of human memory and human error from the most critical configuration decisions.
Which is exactly what you want when you're managing enterprise systems.
We saw today how easily a seemingly minor change to a single local variable representing a subdomain can trigger the complete, irreversible destruction of a cloud environment. So I want to leave you with a complex architectural concept to ponder as you build out your own landscapes. Think deeply about the implications of this destructive lifecycle when you start managing highly stateful resources, like actual in-a-cloud databases or massive event streams inside those subaccounts via Terraform. How do you design your Terraform state boundaries?
That's the million-dollar question.
How do you partition your architecture, perhaps breaking the sub-account creation into a completely separate state file and lifecycle from the database creation, so that a simple, innocent update to a naming convention doesn't accidentally trigger the destruction of your entire production database? Navigating that blast radius, designing those isolated state boundaries. That is the true defining challenge of enterprise infrastructure as code.